going to start off with some slides about divergent transitions, and then we'll go back and forth between this and some code to see how this works. So divergent transitions are a warning that you may get when running a stand model, and they are one of the warnings that you really should be somewhat worried about. You're not going to want to ignore. We talked in the first week about Hamiltonian Monte Carlo and about how there's the theoretical, that Hamiltonian Monte Carlo is analogous to throwing a ball over a surface, or how a satellite orbits in space with gravity around some object. And there's both the theoretical path, which is shown here in that brown line with the circle at the end, but what we need to do is numerically approximate that path as part of the dynamics, and doing that is hard. And there can be times when our numerically calculated path diverges from what we think is the true path. And that's shown here in that green path is numerical path. And if that numerical path deviates from the true path based on various diagnostics within the algorithm, Stan reports a divergent transition. So what are some causes of divergent transitions? So funnel geometries, we call them, in the joint posterior shape is probably the most common, and we will work with one of those in an example. Secondly, very strong parameter correlations, very heavy tails or curvature in the posterior, or very different parameter scales. So some parameters are really, really big, some parameters are really, really small, that your parameters aren't roughly on the same scale and roughly around, a unit scale, so around 1. That last one's probably the easiest one to fix. You can scale your data, or sometimes you can just scale your parameters. So instead of modeling some parameter b, you might model your parameter b divided by 1,000 within your model. So the last one's probably the easiest one to deal with. The other three can be harder to deal with, and the first one is probably the most common one that you'll see that you need to deal with, and that's what we're going to work with. So divergent transitions are both a curse and a blessing. So they're a curse in that using Hamiltonian MCMC means these can happen, but they're a blessing in that they are a useful diagnostic, that our sampler is missing some part of the posterior. And although divergent transitions themselves are unique to the Hamiltonian MCMC, similar problems can arise with other MCMC samplers, and most other MCMC samplers lack such a diagnostic that there's some part of the posterior that they're not exploring for some reason. So we're gonna look at the code in a second. But first, how do we fix divergent transitions? We'll talk more about this as we look at the code, but one is to increase the app delta. So we talked about that. That's your target acceptance probability. It's sort of the one main dial that we have to tune the MCMC. So as that goes towards 1, it's going to take generally smaller and smaller jumps to make sure that it has a higher acceptance probability in the MCMC algorithm. And by taking smaller and smaller jumps, it's going to better be able to navigate trickier parts of the posterior at the expense of speed. Scale the data parameters, so they're roughly in the same magnitude. Reparameterize the model, and that's a big one, and that's what we're going to look at in the code. You can make the priors more informative or collect more data. We'll talk about that. Or you can simplify the model, add more data. So there's this figure in the Bayesian workflow, preprint and paper, that illustrates that issue with adding more data or a stronger prior, and that it can affect the posterior geometry. I'm going to jump away from this and go over to the code, and we'll come back to this once we understand what we are modeling. So I'm opening up 11-divergenttransitions.rmd. And what we're going to work with is one of the most classic Bayesian data sets. It gets used all the time in examples for Stan. It is I think the main example in the, if you do the question mark Stan. It's a simple data set, but it creates all sorts of interesting problems from a statistical perspective. So it represents the test of coaching program for the SAT scores across 8 schools. So it's often called the 8 schools example. And the response, y, is the average improvement or not of a test score for a given school. And then sigma is the standard error on that average improvement. So the data that we're modeling is quite simple. We just have the number of data points, 8. We have the average improvement. In the cases of a negative, they actually got worse. And then the standard error on that average. And the idea is to ask overall, did this coaching program improve SAT scores? So we can fit a hierarchical model that partially pools information across schools. And the typical model that's fit hierarchically basically has this true latent, so like unobserved true score for each school, of which this is an observation of that, based on the standard error that is given. And then there's some variance of those improvements across schools. So let's go back over to the slides where I've got a color-coded version of this model. So our model, and jump out of this so I can point to it. This is what our model looks like. We've got our data section parameters model. In our data section, as we said before, we're bringing the number of schools, some integer. We're bringing in the mean score change. It's a vector. We're bringing in a vector of standard errors in sigma. In terms of what we want to estimate, we have an overall across school average improvement. This is our main parameter of interest. We have sigma prime, as it's called here. So that's the standard deviation of those underlying random effects or latent underlying true score values. And then we have those random effects or unobserved latent underlying score change values called theta. So the main part of the model is just here, second last row. So we're saying that these unobserved true scores are a function of the overall average and the spread of those unobserved true scores across schools, sigma prime. And then we have the observation error on those latent school scores and the input observation error. So sigma here is input as the observation error. Sigma prime is being estimated, and that's the spread of those latent scores. Mu is the overall average. That's what we care about. So it's a random effect model. We're inputting the observation error. Otherwise, it's basically like a random intercept model where we're inputting the observation error. So what I have here is that stand code in the RMD file. And if we fit this simple model in Stan, which I can do here on line 55, I get all sorts of warnings. It says there were 71 divergent transitions after warm-up. See this website to find out why this is a problem and how to eliminate it. This is a very useful website that it is worth going to. It has a lot more than just divergent transitions, but it describes divergent transitions. But it also describes all the other types of warnings that you might get, what they mean, and how you might fix them and how concerning they are. So it also suggests that you could use the pairs plot to diagnose the sampling problem. And if we did that on pairs of mod 1, make our figure size bigger. So each of the diagonals here is a thing that the MCMC sampler is keeping track of. So we've got our overall mean mu, sigma prime, all of those thetas, and then we've got the samples jointly between, sorry, this is flickering on and off, but we've got the samples between each of those parameters, and then in the lower triangle, we have these red dots, and these red dots, maybe it'll stop flickering now, are where we have divergent transitions. So here, a lot of these parameters, these red dots, are just they're in the center of the posterior. But the key part, as we're going to dive into, is what's happening here with sigma prime, how all of these are sort of clustered at one part of the posterior. So that ends up being concerning. It means that the sampler is not getting to part of the posterior. So if we wanted to check that through a function as opposed to just the print statement, there is also this get num-divergent function, and that gets us 71. I'm just going to turn off my graphic device. And if we had launched ShinyStan, we would also be able to inspect that, and you'd see these highlighted red dots where you've got divergent transitions. So let's make this scatter plot. What I'm going to do is just basically zoom in on one of those panels we saw in the pairs plot by using the MCMC scatter function from Bayes plot. I'm extracting the MCMC samples as an array using as.array on my model. The common place where you see these divergent transitions is between one of the random effects and the standard deviation that describes the spread of those random effects. So that's why I know to look at this. So I'm taking the first random effect value, theta1, and I'm going to plot it against sigma prime, which is the spread of the random effects. I am going to log transform sigma prime. You'll see why in a sec. It just stretches it out so you can actually see what's happening. And then there's this argument NP, and if we look at the help for MCMC scatter, see NP is null. And if we scroll down, so it's a data frame of nuts sampler parameters to plot. And so if we run this function, let's see what comes out of there. This creates a data frame with statistics on the no U-turn sampler parameters that MCMC scatter grabs and colors dots by. So you can basically just copy and paste this code. But if we run that NP argument, what it's done is it's colored the dots here as divergent transitions because I passed this in. So this is the log of the standard deviation of the random effects on the y-axis. This is a single random effect value, a single underlying assumed latent change in SAT score for the first school. And we get this, you see the start of a funnel here where it's quite wide at the top and gets narrower at the bottom. And you can see all these red divergent transitions that tend to be happening towards the bottom of the funnel. So this is the classic funnel divergent transition problem. So the solution to this is changing this model the way that it's parameterized in the stan file. Let's go back over to the slides. So this was the model that we fit. This is the same model, but I've just removed the comments from it. And in the next slide, everything that's commented and highlighted is going to be what has changed. So data have not changed. In the parameters, we have added a vector called eta. So before we had theta. So now we're actually tracking a thing we're calling eta. Theta still has the same meaning, but we're creating it from eta in our transform parameter section. So now we define theta in the transform parameters. We say theta is equal to our mean plus sigma prime, same meaning as before, times eta. And eta is defined as a standard normal variable in the model. I know this probably seems crazy. I have to go back to this every single time I have to do it. But what we've done is we've totally changed the geometry of the problem so that the sampler does not see a funnel, and it fixes the divergent transition problem. So this was the original, where we just stuck mu, our mean, here in the model, and sigma prime here on this line. So theta was sampled from overall mean and its spread. Instead, we do that here on this line. So now theta is being formed as a function of a standard normal times sigma prime, because if you just multiply this 0, 1 normal variable by sigma prime, it therefore gets the spread of sigma prime. So we're creating theta as a transform parameter, but the no U-turn sampler is actually tracking eta, sigma prime, and mu. So why does that do anything that we want it to do? Well, this is a nice visualization that Cole Monahan has in a paper about 10 years ago now. So this first panel here is what we were looking at. It's the same thing as what you're looking at here. It's just turned on its side. So this is log of sigma on the x-axis. This tau here, this is our theta. So you have this funnel. Those are those divergent transitions. The same things that we see here are right here. And what's happening is when the sampler gets here and it has these divergent transitions, it is not going fully into the tail of the funnel of the posterior. So this is the actual distribution here. But we're not seeing everything left of this dotted vertical line. And so we would have a biased parameter estimate. And the degree that is biased is the degree to which the tail goes off to the left that it's not seeing. So that sort of naive parameterization, which is the centered parameterization that we talked about first, created this. This second version, called a non-centered parameterization, was originally called the Matt trick, because Matt Hoffman came up with the idea, I think, in the STAN community. But they call it the non-centered parameterization. That creates this here. So this on the y-axis would be the equivalent of our eta. That is this thing right here. And we still have log sigma on the x-axis. And because our eta, here, z, is a standard normal variable, it's not correlated with log sigma. So we've broken that funnel shape. And the sampler sees this nice cloud of points. It has no problem sampling from this. And internally, eta gets transformed back to theta so that the actual thing that we're modeling still has this funnel, but we can get way down here into the tail of the funnel because we have sampled from it like this. Are there any questions about this? I know it's a lot to take in. Having worked with this for, over 10 years now, I still have trouble wrapping my head around it, but it's an important concept. If you're fitting your models with BRMS, they are set up, as far as I'm aware, as non-centered to start with, so you often won't have this problem. But if you're coding your own models that have random effects, that they're hierarchical, it's very common to run into this. So you very commonly have to switch to a non-centered parameterization, which basically means staring at a model like this, doing the same thing to your model, and seeing if it fixes it. Are there any questions about what's going on here? Okay, so one of the things that we mentioned as well earlier is that the degree to which this is a problem is affected by how much information is in the data or the prior. So the amount of information in the data or the prior affects the shape of the posterior and therefore affects the degree to which you would expect to get divergent transitions. So part of the reason I think why this 8 schools example is a good example to show divergent transitions is because there's only 8 schools. So there's not a lot of data. And there were also the priors in the model were quite weak. So this is an example, I think it's actually from the 8 schools example, and it's in this preprint. So on the right, you've got samples from a posterior. I guess it's not exactly the 8 schools example because they've got more schools. But if you've got here, there's a sample size of 6, sample size of 9, sample size of 21. And as you increase the amount of data, the posterior becomes less funnel-shaped and starts approaching the normal distribution. It starts to be better behaved like this. And so the sampler now has no problems sampling from it. Over here on the left, this is like a density representation of that joint posterior shape. You can see how it goes from being very funnel-shaped, here being cut off because all the divergent transitions, it wasn't actually going down in there. And then it starts to become more and more symmetrical and less funnel-shaped. Similarly, if you had put stronger priors, say on log sigma, or maybe elsewhere in the model, if there's more information in the priors, you can also change the shape of the posterior and make it less funnel-shaped. So that's another solution. And of course, if we had changed adapt delta, the sampler would be taking smaller and smaller jumps and would better be able to make it down into this part of the funnel. It might not make it all the way, depends how bad the funnel is. And we can play with that over in the code. So before we fit the centered version, now we're going to fit the non-centered version, which is what I have right here. So I've got eta, my theta, my school latent effects, the random effects, are the mean times the standard deviation times the standard normal eta. Eta is defined as standard normal. These have quite wide priors. So if I fit that model, so it's better. You have only 2 divergent transitions, which is still worrying. As soon as you have any divergent transitions, it means that there is potentially a part of the posterior we are not seeing. So we might still have a problem. We shouldn't ignore even 1 or 2 if at all possible. But we're obviously in a much better place. If we use the scatter plot, you can see now we've only got 2, and the other important thing, and we might want to check it against the other theta values, but those divergent transitions are not at the edge of the joint posterior, so it's not evidence that maybe there's a bias happening. They're just kind of randomly in the scatter. We can still do better. And the most obvious thing is to slightly increase that adapt delta, which is that target acceptance rate. So the target acceptance rate by default is 0.8. And if we increase that towards 1, we'll take more careful steps to have a higher acceptance rate based on the tuning in the warm-up stage. So commonly you might increase that to 0.9 or 0.95, maybe 0.99, extreme circumstances maybe 0.999. As you get really, really close to 1, the model is going to be much slower to sample from. So let's increase that to 0.95. Now our model fit and there were no warnings. We have saved that into mod 3. So if we look at mod 3, we have lots and lots of samples, high effective sample size, low R hats, and there were no warnings. And if we make our scatter plot, we have no highlighted divergent transitions, and we can see samples going right down here into the funnel with no red dots. So you might be wondering, like, would this actually affect the results that I would get out? Well, yes, it would. We can show that by extracting the posterior from our first model, mod 1, and then our non-centered parameterization that had a higher adapt delta value, mod 3. So that extracts a list. If we remember, if we look at the names of P1, we've got our 3 parameters and our log posterior samples. And then we can plot out histograms. So I'm going to say I want 2 rows, 1 column. I'm going to make this bigger. So in our first model, our samples in log space stopped here just below 0. In our third model, the samples go way off down here, down to -8 or something. And say we were really interested in the mean of our standard deviation parameter. So our mean is substantially different, 1.4 versus 1.1. So because we lost that lower tail of the funnel, because of the divergent transitions, we would have a biased estimate of the spread of our random effects. And they'd be biased throughout the rest of the model. It's just harder to pick out one value to illustrate it. So I've got some material at the bottom you may find useful. This is that reference manual that the warning will actually tell you to go read. This here is that paper that Cole Monahan did as part of his PhD chapter, which is a nice introduction to the Newton sampler and Hamiltonian MCMC for ecologists. That's the conceptual introduction to Hamiltonian Monte Carlo that I have mentioned many times. And then this is a blog post that I think is particularly helpful, working through some visuals of what's going on and so on. So Bayesian workflow. So there's this preprint, I think now paper, Visualization in Bayesian Workflow. I think this was the first big paper by the Stan folks, thinking through Bayesian workflow. So this is how to put together all the pieces that we've talked about in order to run analysis, and thinking about how you can use visualization throughout to accomplish that workflow and check it along the way. There's another preprint just called Bayesian Workflow, which is more about the theory and thinking beyond just visualization. And then, since this is a TESA workshop, there was a paper that Cole Monahan put out recently thinking about how to apply those concepts into data-rich fisheries stock assessment. So there's this definition in that 2019 preprint that practical Bayesian data analysis, like all data analysis, is an iterative process of model building, inference, model checking and evaluation, and model expansion. So what is the Bayesian inference versus workflow? Well, Bayesian inference is the formulation and computation of conditional probability or probability densities. So it's just the technical aspect of doing that. But then Bayesian workflow includes a lot more. It includes steps of model building, inference, and model checking / improvement, along with a comparison of different models, not just for the purpose of model choice or model averaging, but more importantly, to better understand these models. So let's talk about what the components of a Bayesian workflow are. So before fitting a model, we have to choose an initial model to start with, possibly scale and standardize the data, which we've done throughout several examples. We may conduct some prior predictive checks based on our understanding of the system and the rough scale of the data that we know is possible. We then fit a model. We need to select defensible MCMC chain settings. We've talked about that throughout. But we need to work in a way that we can fit models quickly when experimenting. So that means we may experiment with just one chain and a few hundred MCMC samples so that we can fit rapidly our models before deciding on our final model. So we don't want our chain settings to inhibit our ability to quickly experiment. We want to use simulated data where possible to find problems. So that may mean simulating fake data to test our model, to find coding errors, to find estimation issues. We might be simulating from the model, or in a perfect world, we would actually be simulating from a totally separate code base so that we can make sure that our model is coded correctly as well. So that might mean simulating from some R code and then trying to estimate the known parameters based on a stand model. We then may need to address computational issues. So that those divergent transitions were a computational issue that we just talked about. And how do we do that? Well, we generally start simple and we add complexity step by step so we can understand what that complexity does to our model and to our computation of the posterior from that model. We want to document the process of expanding our model, all the models that we've done along the way, as much as we can. And we need to adjust our priors and simplify our models as needed to make sure that our model is at a level of complexity that we have faith that we're actually estimating to our posterior as we would like, but that represents the important aspects of our data. We then evaluate model fit. This is through things like posterior predictive checking, which we've talked a bunch about. Cross-validation, we talked a bunch about that last week. Assessing the prior contribution, so that might mean refitting the model with a few different priors to understand the impact of the information in those priors on our posterior inference. We then need to summarize the inference. We've done a bunch of that. We might summarize that graphically as the full posterior distribution. We might summarize that in terms of the probability of a parameter being above or below a certain threshold or within a certain range, or as credible intervals and means. And we need to iterate through this as needed. I think this is a great graphic in that Bayesian workflow preprint. The idea is to find problems that can be identified somewhere between the simple models that we can fit and the complex models that we can't fit. So we start with really simple models that can be fit successfully. We add complexity and build understanding as we add complexity. At some point, if we get too complex, we have models that we can't fit, probably for computational reasons. For example, divergent transitions we talked about in the last stage, or models where the sampler just cannot converge in any reasonable amount of time. We want to end up somewhere along here between the simple models that we can fit, the complex models that we can't, at a level of complexity that captures the important aspects of our system. This is a figure that they include in that preprint. I think this is a great aspirational goal of where we might get to, but probably more than most people are going to do. But it's a wonderful visualization of honesty in everything that's been tested in a given Bayesian data analysis. So on the y-axis, top to bottom, we've got different hypotheses that are being tested. And then in the panels from left to right, we have a frequentist model, we have the main Bayesian models, they have secondary Bayesian models, and then they have Bayesian models that had problematic fits that they don't fully trust. And then as you go from the x-axis left to right, there are different models there. So they have different predictors included in them. And then the color coding corresponds to the p-value for the frequentist or the posterior probability of that hypothesis being true for the Bayesian models. So you can see everything they've tried, and they're being honest about that. And they're being honest about ones that had problematic fits, did not have problematic fits, what are their main models, and so on. And often in stock assessment, we end up in a situation kind of like this, where we have fit, say, a dozen different models, and that type of thing could potentially be visualized in this type of way. So you don't have to do something quite like this, but I think this is kind of an idea we could strive for. Okay, so the last RMD we're going to work through is 12 workflow-sdm.rmd. And what we're going to do is we're going to work through a full Bayesian workflow of an applied problem to look at how this works in practice. So this should bring together everything we've talked about throughout the course. All right, I just restarted my R session. Control-Shift-0, Command-Shift-0 on a Mac. So I'm going to load some libraries. We're going to use BRMS. We're going to set up parallel cores by setting the mc.cores option. As a reminder, if you ever forget that, like I always do, as soon as you load rstan, you would get that. You would get that little thing here about setting MC cores. I'm going to set this option so that my BRS model doesn't refit for me unless I change the model, and that's going to help this run quickly for me so I don't have to sit here and watch each one recompile. And I'm just creating a cache folder that I'm going to store those BRMS models in by supplying that to the cache argument. So not essential, but it makes this example a little nicer, and it's probably what I would do in practice. So the data we're going to work with are these rockfish biomass densities from this fish survey we run the Pacific coast. One of the legs of the survey just went out yesterday, actually, on the Hecate Strait. So it's the groundfish bottom trawl synoptic surveys in British Columbia. I'm including density only for tows that did catch the rockfish of interest. In other words, I've removed the zeros just to keep this example simple so we can work with Gaussian observation error and not work with a delta or a hurdle model and worry about the zeros and the positive parts at the same time. I'm going to keep this example simple by just working with the positive densities. So let's load the data. Actually, let me just read in the first line again. So if we use glimpse from dplyr, so I've got just over 1,400 rows of data. I have a species name, so there are 9 species of rockfish that I've included. I have the year that this survey observation came from. If we look at table year, so there's years from 2004 to 2022. This for any given, the survey has 4 different regions, and any one region is run every 2 years. And we have density in kilograms per meter squared of the species. So that would be the weight of the species divided by the area swept from the tow. We have depth in meters, and N, which we're not going to be using. So I'm just going to create some other columns here just to make the code easier to work with. I'm going to create a scaled version of depth. So that goes scaled by its standard deviation and centered. Scaled version of log depth, sorry. So I'm going to log depth. That's just going to spread out the quadratics that I'm going to fit so that they better fit the data. I am going to create a F year, which is a factor version of my year, just to clean up my code and not have to write factor year all the time. Similarly, I'm going to create a factor F species of species common names. So I don't have to write factor species all the time. And I'm going to scale my density just to make these values not really, really tiny. If we look at the mean of, because of the units, they're really small values, and that could create coefficients that are small, really small in magnitude and create estimation errors. I'm going to multiply that by 1,000 just so that I'm working with something that's not so tiny. So now I've got a mean of 0.54. So let's plot the data, which we always should do. I'll start by just plotting it in several different ways. So this is all the data together, all the species, all the years. I've got log depth on the x-axis and then log density for all the species combined. And then I've put a smoother through it using MGCV just to visualize what's happening. So there's this scatter shot, and there's maybe a little bit higher here in the middle. Here I'm doing the same thing, but I'm coloring by species. So we can see that there's some overlap, but there's some differences between the species. And then I'm making the same plot here, faceted out by species. So it's a little easier to see what's happening for individual species. So we're going to try to fit this shape. Our question is sort of, how does depth relate to the expected density of these rockfish? You can see that we've got this sort of curved shape where there's some kind of an optimal depth for a given rockfish species. So we're going to have to fit some kind of a curve to that. We're going to end up fitting a quadratic to get that shape. And we're going to be working with log density so that our predictions are always going to be for positive density in the end, so we can't have negative densities. And that also means that our predictors act multiplicatively on density as opposed to additively. So for a unit change in x, we're causing a multiplicative change in expected density. So the first thing we need to do, now that we've done a little bit of data exploration, we have an idea of what we're working with, we need to think about some prior predictive checks. So we looked at this before with BRMS. An easy way to figure out what are the priors that BRMS is going to use is to run default prior on our formula. So we're going to be modeling the log of density with an explicit intercept, so it's not doing the mean centering inside the model as we talked about. With a predictor of log depth and then log depth squared, we have to protect that with a capital I, which is just identity. It just tells R I actually want the square of this as opposed to the interaction with itself. So this lets us get that. We could have done this with poly log depth, comma 2. That would have worked as well. But I'm writing this out here to be explicit about what's happening. So let me make this big again. To the best of my ability. So we're going to have priors for our intercept, priors for our log depth squared, log depth, and sigma. So it's getting hard to read because it wraps around sigma. So the standard deviation on the observation error, which we've got as Gaussian, is going to have some prior as well. The default priors here are flat, so there's basically no prior input. It's negative infinity to positive infinity uniform, which is probably not great. So we're going to specify some priors ourselves. So what we can do is we can think about some priors and we can sample from the priors and then see what data would look like if they came from those priors. So a prior predictive check, as we've talked about. We talked about before, the way you can do that with BRMS and the BRM function is to tell it to sample from the priors. And here, because we're just doing a prior predictive check, we don't even want to bother fitting the data. We're going to say sample prior equals only. We have our same formula as before. This is where I'm going to cache the model. So unless I change it, it's not going to recompile and refit my model. And then I've set some priors here. Now, because for the purpose of this, I just want to focus on the curvature of the fit. So I'm going to set the intercept to roughly the mean of the data. And I have mean centered the predictor. So if I do mean of d density, so because I've already mean centered my predictor, I would expect my intercept to be roughly this. So I'm going to set my prior to match that so that I can focus on other aspects that are harder to get right in terms of my priors. So I'm going to start with a normal 0,1 prior on log depth, normal 0,1 prior on log depth squared, and I knew what to call that based on what came up in that default priors table. So I'm copying log depth here, I log depth capital E2, because that's just what BRMS does with my quadratic term. If I hadn't specified the coef, I could also have just had one line, right, like this. That would do the same thing here. This lets me have different priors for different fixed effects. Here they're the same. And then here is the prior I'm putting on sigma, which is similar to the default. I've just rounded the scale to 3 instead of 2.5. That is all. So it's a student t, half student t, with a degrees of freedom of 3 and a scale of 3. And I will fit that. So let's look at what we just did. So we have, what I've done is I've filtered my data just for red-banded rockfish. I'm just going to pick out one species to make this easier to think about rather than thinking about all the species all the time. I'm going to create a data frame here that I'm going to append my prior predictive checks onto. So I've got my real data and my simulated data from the priors. So to start with, I'm just creating a version of data here. Where I'm going to match the format of what comes out of my prior predictive check. So I've created a column called dot prediction because that's what it's going to be called. I've named this draw 0. So this is the very first draw, and this matches the format of what comes out of TidyBay's predicted draws. So if I run that and I look at what comes out, you'll see here I have taken 8 draws from my model, which was the prior only. The value of those draws is in my dot prediction column, and the draw number is here. So I've just matched that, but here it's the real observations. So all of that just to be able to make this type of plot. I guess I haven't actually bound them together. I should have, but I didn't. So this is just the priors themselves, and if I did this right, I could bind rows obs 3p. Let's see if this will work. There we go. That was my intent originally. So now the first facet 0, these are the actual observed data, and the other ones are the prior predictive simulations. All I did was just combine those two data frames as I meant when I first wrote this code. So we've got 8 simulations from the prior, and our real data is panel 0. So that's not looking too bad to me. The scale is not dramatically off. Sometimes we can have data that are considerably more dispersed, but not ridiculously so, not thousands of times more. So, and some of our simulation draws do resemble the data at this scale, at least. So those are posterior predictive draws. Those are new simulated observations from the prior, but we can also look at new expectations from the prior. So that would be sometimes called a prior push-forward simulation that we talked about. To do that, we can use the EPRED draws instead of predicted draws in the same format as before. So now I've taken 9. And so now there's no scatter because this is not adding on the observation error. This is just the expected values. So it's basically just drawing those curves, those sad faces or happy faces or straight lines out of the quadratic portion of our model. And so we have some that are curved up, some that are curved down. Now you might be thinking, well, we know they can't curve up, or we want to have a fairly low chance they could curve up, and that would be a reason that maybe you want to put a more informative prior on that quadratic term. You could have a prior on the quadratic term that has a negative mean to help induce the model to create the sad face shape. So that's something you could do, perhaps based on some meta-analysis or some previous analysis across other species from some other survey or elsewhere in the world or something like that. In practice, that can be hard to justify, and so often we would probably just have a mean-centered prior that at least doesn't allow the curvature to be too extreme one way or the other. Sometimes you might actually expect there to be some upward curvature, like if you're only looking at a portion of the depth range of a species, you might just be looking at part of the hump of that relationship with species density and depth. So you might actually expect there to be some times to have these upward smiley faces. So we don't want to totally rule those out. So what if we had much wider priors? So those ones were standard normal, so they were 0, 1 standard deviation or variance priors. So let's try one where I'm going to set those priors to have a standard deviation of 100. And I'm going to let the scale on the observation error be much bigger as well. So 100 instead of 1. I'm just taking 100 iterations because I don't need that many iterations here. I'm just going to take samples anyways. So again, I can take my predicted draws. This time I actually did bind on my observations like from before. And I've also gotten fancier here and colored my draw zeros differently from the rest. So now we can see that the scale is really, really different. So on the scale of the variation we see across our 8 prior draws, our observed data are basically just a totally flat line because our predictions are going from positive 1,000 to negative 1,000. So we've gone well beyond what I think is remotely plausible in our data. So we would not consider these weakly informative priors. Now it is true if you had a lot of data and you didn't want to really have much of a prior influence at all, you might go with priors like this, but this would not be consistent with weakly informative priors and that whole philosophy. Okay. So we've done some prior predictive simulations. We have faith that those priors that we initially picked can create wider spread in the data than what we've observed, but not values that we would deem just completely impossible. And density from surveys is probably a slightly more abstract quantity to think about, so it's helpful to look here at the actual data. In other cases, you might have response variables that you understand better, and you actually know beforehand what ranges of that value are possible. Like if you were modeling fish length, you have some idea about fish lengths conceptually in your head. So let's start by fitting a model that is similar to that prior predictive simulation we did with the weakly informative priors. The difference here is I no longer have that sort of tweaked, more informative prior on the intercept. Instead, I've just given it a wide scale, a wide standard deviation. And these are the standard normal priors on those beta coefficients. I'm going to fit that. That's going to take a couple minutes if you fit it for the first time while it compiles and fits. I've set the seed here just so it's reproducible MCMC samples, which is good practice in an applied analysis, so you can get the exact same answer out. You'll see I've only set 1,000 iterations here. As you'll see, I don't really need the full 2,000, and I'm trying to make this faster while I'm experimenting with my models. I might come back and have more samples once I've chosen my final model. So in practice, I think what you would probably do is you'd fit that model, you'd go through the checks and the things we're going to look at, and then you would expand your model and then check that and so on. To keep this example a little more easier to follow, I'm going to fit 3 different models, and then we're going to look at those 3 models in the same way. So the second model I'm going to fit is going to allow the species to have their own curve, so to have their own relationship between density and depth. And I'm going to do that by taking my depth and depth squared predictors. And this is the syntax you would see in LME4, GLM, TMB. So this is saying that an implicit intercept plus these 2 coefficients are going to vary, vertical bar here, according to my species factor column. And there's going to be some estimated standard deviation of the spread of each of those coefficients that varies with species. So, these would be considered random slopes. And there's also a random intercept that's implicit there. You don't need to actually write it out, but you could write 1 plus to make that explicit. So if I try to make this bigger so we can get this on one screen. So close. There we go. So I've run the default priors. So these are all the priors we now need to think about. Now that we've gone into a hierarchical model, there are many more priors to think about. So these are the ones we had before, what we might call the fixed effects. This is the standard deviation of the observation error. That's what we had before. All of the stuff in here is new. So all of these ones here are standard deviations on these, what we might call random effects. And this first unnamed one is just would apply to all of them. And these would be individual ones if we wanted to specify them as such. So we've got a spread of our intercept, the squared term, and the slope term on depth. And then we've also got a correlation term here, and you can see the default is that LKJ prior that I mentioned in the first or second week, which is a common prior for correlations. So it's bounded between -1 and +1. And it's got one parameter to worry about, and the default here is that a value of 1 on that one parameter. And so this is the correlation between the random intercepts and slopes across the species. Okay, so we've jumped in complexity quite a bit in the model, but all of that is just to allow our curves to vary by species. So to fit that model, I plug that into BRM. I've increased my adapt delta a little bit. Hierarchical models are harder to sample from. We're more likely to end up with those funnel shapes and divergent transitions. So often by default, you might just start at 0.9 instead of 0.8. I don't think it really matters too much here for my memory. So I'm going to set the same priors on the main effects, and I'm going to set the same kind of prior, the half student t prior, on my observation error standard deviation and on the spread of the random effects. Those are both the same kind of parameter. And then I am going to set up that LKJ prior on the on that correlation, and I don't actually have to specify this because that is the default, but it's a good practice to specify it explicitly so that it's in the code, it's explicit what you did. And if the defaults change in BRMS down the road, your model will still be the same. So I'm going to fit that model. And now I want to add a third level of complexity that I want to examine, which is that maybe it's not just the curves that vary by species, maybe the spread of densities, so the observation error, is also going to vary by species. And we can do that within BRM quite simply by expanding our formula to include a predictor for sigma, which was, as you remember, sigma is our observation error scale, standard deviation. And with BRM, for these fancier formulas, of which there are many fancier formulas, there is a function BF in the BRMS package, which lets you include all sorts of additional functionality in the formula with a ton of documentation here. So we are going to do that. And if we look at, so this is going to go into the ... part of the BRMS formula. So BRMS formula, BF. So now we've got sigma, so comma, sigma as a function of factor species. So this is going to let the model estimate a different sigma for each species. So we've got that hierarchical model on the relationship with depth, and then we've got the observation error is scaled differently by species. Otherwise, it's the same as before. I'm going to fit that model. That'll take a little while longer for you. I'm going to try and rescale my windows. So we can look at our models. Let's just look at the third one, since that includes everything. Make that bigger. So there's quite a bit to look at here. Obviously, there's a lot more parameters. Tells us what our formula was. And so we start off here by getting information on those random effect hyperparameters, as they're sometimes called. So these are the standard deviation of the random intercept, standard deviation of that log depth slope parameter, spread across species levels. Same thing for the squared term. And then you've got the correlation between various random effects. So you've got the intercept against these slope terms, intercept against these slope terms, and then the correlation between those two slope terms and the random effects across the species. Okay, and each of those has a mean and standard deviation of the posterior, credible intervals. R hats look good. Effective sample sizes look good. They're all well above 400. And we only had 1,000, I think, samples throwing out the first half per chain. Then we get into our main effects, what you might call fixed effects. So I'll just start with these three, which are simpler ones. So we've got our intercept, so when all our predictors are at 0. We've got our log depth effect. We've got our log depth squared effect. All of our hats look good. All of our effective sample sizes look good. And then the funny thing that you might not have seen before is now that we have modeled the observation error sigma as a function of species, we have an overall. So this would be the sigma for whatever species had the first factor level, which I think is alphabetical here. And then the other ones are offsets from that. So this is our first species, standard deviation of the observation error, and then dark blotched is 0.1 lower than that. Red stripe is 0.34 higher than that, and so on. So that's how you read it. If we looked at levels of F species, so the first one is canary, and you can see that canary is missing from here. So this is the canary estimate, and then everything else is offset from the canary estimate. Are there any questions about what we're looking at in the output. Okay. Let me try to scroll back in my tiny zoomed in window. Okay, so we need to look at other aspects of how the models fit. R hats and effective sample size are great, but nothing beats visually looking at a trace plot. There's all sorts of things we can identify that we wouldn't see otherwise. We're going to use that regular expression syntax that I've used before. So the caret here means starts with. So I'm going to look at trace plots for all the parameters in this case that start with b underscore, which are my main effects. Of course, in practice, I don't want to look at all of them. So that's my first model. And this is the third model. And then even those, we've got extra parameters here because those are those observation error standard deviations, which if you look at how they're named, they also start with b underscore because they're also fixed effects. So everything looks great to me. They all look like fuzzy caterpillars. I'm happy with that. I would look at the other parameters in practice. So we can summarize the parameters in various ways. So we might do that visually. We might make density plots like this, or area plots, or interval plots, and so on. You can make those plots yourself with ggplot or base graphics or however you would like. Just on the topic of these, if you wanted to grab the data and maybe make your own plots, for most of these functions, there's also a version of the function that has underscore data. So if I ran this, maybe I'll switch the head to glimpse. This is just the pipe. So this pipes the output into the first argument of this. So that gives me back the data frame that was underlying the plot that I see here. So I could use that to grab the data and make my own ggplot or whatever with it that I want, if I want to customize it. So that's a fast way if you don't want to do the data manipulation yourself. Okay, so posterior predictive simulations, really important aspect of making sure we have faith that our model represents the same system that generated the original data. So we can do a overlay plot. So this is from the first model, the simplest model, just one overall curve. You know, it's hard to say if anything's really gone wrong here. It certainly looks a little bit off. So my simulated draws are a little bit to the right of my observed data. Hard to say whether or not there's a problem there, but we know there's lots of features to the data year species that I'm not plotting there. So let's plot it by species. This is where we first see, oh, something has gone wrong here. This isn't great. We're not capturing the distribution at a species level for all the species. Some species, green striped rockfish looks okay. Maybe I could convince some of the other ones aren't terrible, but some of them are pretty far off. So there's some feature that's not being captured in that first model. As we might expect, we know there's some differences by species. So now I'm going to do the same thing for the second model. So this has different curves by species. So I'll go back and forth. Actually, maybe I'll just take a screenshot. So this is the second model. It's going to be on the left. And the first model here on the right. So some of them, like rosethorn rockfish, looks better now here on the left. So yellowtail rockfish looks better and kind of acceptable now. Dark blotch looks better, and green stripe looks about the same. But some of them still look off. Sharp chin still does not look good. Red banded does not look great. Canary does not look great. So allowing the curves to be different by species has helped, but it hasn't really solved all of our problem. So let's look at our third. Okay, so here's our third one, which has also different levels of noise or observation error by species. So this is considerably better. Let's go back So the original one is on the right. On the left is our third model. So I'd say we're getting into acceptable territory now. There's still some slight deviations, but they generally are plausibly from the same distribution of our simulated values and our observed values. It's not unexpected that they don't fit perfectly. There's some features that aren't in the data. I'd say spatial aspects of the data are probably the big thing that's not in the model right now, but there's also years that are not being modeled. But we've got a much better model here that has different observation errors, different curves by species than the one on the right. So we've learned that there's different curvature and that in particular the level of spread is different between different species. And it's important to capture that. So let's dig into one species to sort of better understand what's going on there. I'm going to look at red banded. So I'm just going to filter my data for red banded. I'm going to do what I did before where I create a new data frame that's going to match my posterior predictive simulations so I can bind them together. I'm then going to use tidy bays to take out some predicted draws. So posterior predictive simulations with 8 of them. Save that to PP1. I'm going to bind my observed and my predicted values. And then I'm just going to do something here so that I have a type column so I can color it. Not essential, makes this look nicer. Okay, so I've done that both for my first model and my third model. Now if I plot out my first model, so this is the one with the shared quadratic. Observed data on the first panel, and we see that there is some curvature in that, but we're not really getting the same curvature for that species in my simulation draws. And we also see in particular that the spread is different. So these are generally have a wider spread than my red banded. And that's what we saw with the importance of the observation error being different. So if I fit from my third model, now the spread of my simulated values are roughly equivalent to my first one. If I didn't have the color on here, and maybe if I didn't put it as the first panel and I handed this to some colleague, the question is, would they be able to figure out which one's the real data? I'm not sure. I think my guess is a lot of people would struggle here, and that's an ideal scenario. It's possible there's a little something happening here that makes it look abnormal, but some other ones also have some outliers as well. So pretty good. We've gotten a lot better. So those were some visual posterior predictive checks. We can also do visual checks of statistics of the posterior predictive checks. So to do that, I'm just going to use posterior predict from BRMS to grab a matrix of for the first model and the third model. So I've got 2,000, so 500 times 4, 500 post-mortem samples times 4 chains across that many observations. So I've got matrices of posterior predictive simulations for fit 1 and fit 3. So I could do things like plot the median here. So this is the distribution of medians from my posterior simulations in light blue, and then my observed medians here in dark blue. And we can absolutely see that the medians alone are not matching up for some of these species. But if I use the third model that has more flexibility, now my observed are always within the spread of my simulated values. Canaries on the edge, but sometimes you are going to get things on the edge, so that in itself isn't too worrying. We could look at the standard deviation. So obviously there's a problem here in our first model. And then here, think for a sec, this isn't very useful. We talked about how some posterior predictive simulation checks are more useful than others. This is not a very useful one, other than it verifies that our model did what it was supposed to do, because we have a fully independent standard deviation parameter for every single species. So we would expect the dark blue line to be perfectly in the middle for every one of these because we have modeled it as such. So it verifies our model doing what we think it did, but it's not a very useful simulation check because we would expect it to look just like that. So instead, we might pick some other measure of spread that hasn't been modeled to check. So we might do something like take the interquartile range. To do that, I'm going to create a little function, takes a vector, and then calculates the interquartile range. And if I did that for my first, again, doesn't look great. If I did that for my third model, so now we actually something more useful. So we can say that the spread of the interquartile range does vary, but it looks generally reasonable. There's a couple sharp chin is off by a bit. There must be some skewness in the data there, but not too bad, much improved. So the other important thing would be to plot our simulations against variables that were not included in the model. So let's just do a simple one here from our simplest model, and I'm going to group by year to ask, should I perhaps have included year? And so we get this, and the main conclusion I would take from this is that no, probably not. So there's some years, 2010, 2018, that are slightly extreme compared to the constant simulated values, a bit higher and a bit lower than expected. But generally, they are within what we would expect from the simulations. There does not appear to be some strong year signal in the data. So you want to plot these against variables that are in the model, plot them against variables that are not in the model but could have been. Okay, so we've satisfied ourselves with some posterior predictive simulation that we have. At least our most complex model is a model that can capture important aspects, as we've defined them, of the properties of the data. So we have some faith in that to represent our system. So now we could also compare our models with that expected log posterior predictive density, the leave one out version of it that we talked about last week. So to do that, I can calculate that with the leave one out function from the leave one out. It's coming from this lu : lu. It's coming from the lu package. And then use lu compare to compare them here. And remember that higher is better for the expected log predictive density. So fit3 has a substantially higher ELPD, and the standard error on that comparison, so roughly plus or minus 2 of that is a 95% credible interval. So we have substantially better leave one out predictive performance of fit3 compared to fit2 compared to fit1. Makes sense just based on what we saw with the posterior predictive checks. We looked at this briefly last week, but we can also look at the point-wise leave one out predictive ability. To do that, I can just grab this column from the point-wise output from my lu object. Just got to copy and paste that. Now I can compare one model to the other. So I'm going to start by comparing model 2 to model 1. So if it's above, then it prefers model 2. If it's below, it prefers model 1. So you can see, especially here, going from the one that has below the line is favored by having a common curve, and then above the line is from the model that favors having separate curves. So we can see here a dark blotch and sharp chin, for example, that there's in green striped that at the sort of the edge of the curvature, there's not enough curvature probably in the overall model. And so it's doing a much better job of predicting those by having independent or species-specific curves. And then we can ask, well, what happened when we added the observation error being independent by species? So for some of them, it didn't make a huge difference, but for some of them, like sharp chin, red stripe, stuff above the line here that's far above the line was much better predicted out of sample by having that more complex third model compared to the second model. Okay, so now we need to visualize our model predictions. I'm going to do that the same way I've done it throughout. I'm going to create a data frame that has a sequence of values of my predictor that I want to look at. while holding other predictors at some constant like average value. Here I've got one predictor and different species. So I'm going to look at depths across a sequence from the minimum to the maximum of 100 length just to have a smooth curve. So that creates my data frame ND. I'm going to pass that as new data to add my expected predicted draws from tidybays with my fit. I want to take 50 draws, and I'm just going to draw 50 curves. So that's my expected log density across that gradient of scaled log depths for each species. So instead, we might want to summarize credible intervals, and we can do that by creating a, let's look at what LPRED is. LPRED is a matrix, because it's from the BRMS output, so it's creating a matrix, LPRED, of number of samples down the columns, and then number of predictions along the y-axis. So I've got 900 elements of ND. And then we can use that apply function to go column-wise in this case, because we want to go down those 900 columns, and take the median, and take the upper and lower 80% credible interval in this case, 0.9 and 0.1. And then I can just plot them like that. And I'm making sure in this case, I'm going to exponentiate my lower, upper, and my expected value right here, the median, to put this back on a density instead of a log density scale. So it sort of changes the shape of my curves. So now we've colored them by species. We've used geom ribbon to add our credible interval and geom line to overlay our expected value. And so now these are the mean and credible intervals on the expected predictions, the expected values across species. And we can see different widths, different curves for different species. So that's the expected values. And of course, we've talked throughout how you can take posterior predictive values themselves. So now I've used posterior predict instead of posterior EPRED. So that's expected predicted values. These are the predictions themselves of new observations. Done the same thing, but there's much wider spread now, of course, because we have the spread of new observations instead of just the expected values. So now we're really seeing the impact there of having higher observation error. So species like sharpchin that we've talked about before have a much wider spread of possible densities. There's a lot more variation from toe to toe in terms of how much density you see of sharpchin. Okay, so that is sort of a complete workflow for this problem. So we can conclude that if we're going to include these in a model, we probably would need to have variation in the relationship with depth for these species across species. Different levels of observation error was really important. We might put a lot of what we've done here into a supplement. Some of this would just be for us to make sure that we have faith in our model, but we'd want to show sufficient posterior predictive checking to convince a reader that they can buy into our final model at least. We would want to note, at least in a supplement, about what were the models that we used to build our understanding along the way, and how did our inference change as we went. We'd want to write out the equations for our full model. We'll talk about that in a sec. And what might you consider adding to the model? I think spatial term is probably the big one. So depth alone isn't the only predictor of species density. The next main ones I would think of would be space and time. So there's probably some correlation in the residuals that we haven't dealt with. And then some possible uses for the posterior predictive simulations. Well, we've actually have used this type of model for survey design. So now you have a model that could predict new observations of density for a given fish species, in this case, at a given depth. And if you had a spatial term, you could make even better predictions. But right now, you can predict based on depth, new possible observations at new locations that you could then look at different survey designs and see how well they could recapture the true underlying biomass. Are there any questions about that?
I think the one piece I'm kind of hung up on is when I'm thinking about creating plots showing relationships between variables, whether or not I should be using the new observations or the ePred values. And yeah, I'm trying to weigh those back and forth.
Yeah, it's a good question. I think most people are used to seeing the expected values. That's what you get out of GLM or any maximum likelihood methods are generally going to show the expected values, and we're often interested in the expected values. There are certainly some Bayesians who I think would focus more on the observations. There's no right or wrong answer. Depends what you're focused on. For posterior predictive checking, by far it makes most sense, I think, to think about the observations, because then you've got data to compare against. But when you're trying to show a relationship, like in this case, I would probably be showing the expected value relationship. On the other hand, if the focus was on something like a new sampling design of a survey, then I might be focusing on the posterior predictions themselves, because that includes all the noise that is of interest. So they're both valuable. It just depends what you want to convey. If I wanted to convey the different depth relationships with different species, showing a plot like this really emphasizes the different level of observation error. And maybe if that's of interest, then that's what I would show. But if my interest was in the different relationships with depth, this shows that a lot better, because in this case, the magnitude of observation error just dwarfs the shape that I'm interested in. So that's how I might make that decision. But I think in general, I would tend to show this. That's what people are used to seeing. And I would use these types of things more as part of model checking, or if the output is of interest. But, yeah, it's a good
That's really helpful, actually, like to think about those different scenarios. I appreciate that.
So I'm not going to go through it, but just so you know, there is a file, 13-resources.rmd, where I've collected a whole bunch of links. And a lot of these we've talked about throughout. There's probably some that I haven't, but this is here for your use. It's annotated. I have some slides that I'm going to go through next to sort of cover this material in a more graphical way. So, final remarks. Okay, so this is kind of a hodgepodge of closing remarks that I've thought I would think about in terms of everything we've talked about so far. So how many iterations and chains? We've talked about this off and on throughout. I'd say for a final model, usually at least 2,000 iterations across at least 4 chains. You might need more, but not too much more. If you need, 4,000 iterations, 8,000, okay. But if you're starting to get up into tens of thousands or hundreds of thousands of iterations, you're probably not doing it right. At that point, you probably want to think about simplifying your model, reparameterizing your model. There's probably something computationally that can be improved rather than just throwing more iterations at it. It's totally fine to develop and test your models with much fewer iterations than that. So you might have 2 iterations, 1 chain, maybe even 100 iterations, 1 chain for a really slow model, just for when you're experimenting, playing with your models. How should I write my models? Let me just go back and remind people, this is for Stan. Stan is using the Hamiltonian, the no U-turn sampler, which is very efficient for each sample that it takes, but very slow to take each sample because it has to do all the calculations of the gradient and so on to throw the ball over the surface in order to make a good MCMC sample. This is not true at all if you're using Gibbs sampling or Metropolis Hastings. There you might be looking at hundreds of millions of samples, totally normal. Each sample's a lot faster, different ballgame. So we're talking about Stan here. How should I write my models? there's lots and lots of ways. Let me just show an example here of some way that I might write a model. So this is coming back to the linear regression that we've talked about throughout. I've got the BRS syntax at the top. So I've got my model, I've got my priors, and then I've tried to translate that into equations at the bottom. And this should look familiar. This basically should look like the Stan model code, because that's all we're writing out here. We're writing out here first that the data likelihood. So I've got the process part, the intercept plus the slope times my predictor. I've got the observation error variance. Remember that Stan works with standard deviation, like the R functions. Statisticians like talking about variances instead of standard deviations. So you either need to put variances in your normal distributions, or you need to be very explicit in your text that you are writing standard deviations and not variances. So that's something to navigate. But you might say something like this. So my response y indexed by I comes from normal distributions. That's my data likelihood. And then I've got a sequence of priors. So I'm defining my priors for each of my parameters. And then I would write out afterwards what I am showing in equation form. This, we're going to come back to this. So this is the proportional version of Bayes' rule. Coming back to the first day, everything we've talked about, this has been fundamental to it, and a reminder of how you read this. So P, the probability of theta. Theta is often used in statistics to mean the parameters, all of the parameters. So the probability of the parameters given the data is proportional to the probability of the data given the parameters times the probability of the parameters. And the thing on the left is the posterior, joint posterior if we're talking about many parameters. That's what we've been talking about, trying to get to the whole course. And that is proportional to the data likelihood times the prior probability. So, building up your model like I did before, writing it out, I think that is sort of the bare minimum and is great and should be done. This book, Bayesian Models book, is a fantastic book in many ways. I'll talk about that again in a sec, but one of the ways that it's fantastic is in thinking of it. They think a lot about, or write a lot about, how to write your models. And they go so far as to say that every Bayesian analysis should have somewhere the conditional distribution written out, even if it's in a supplement, even if it's in an abbreviated form like this, which we'll walk through. It's important to include this. And for a simple model like this, you might look at it and say, well, this is trivial. What's the point of this? But I promise you that when you get into more complicated models with more parameters, and especially with hierarchical parameters, it's very helpful as a reader to be able to work your way through it and figure out what depends on what. So for the same linear regression here, I might write it out like this based on this syntax. I might say we use the notation square bracket A given B to describe the conditional distribution of A given B, using bold symbols to refer to vectors, which is common, or bold to refer to matrices. The joint posterior distribution for our model can be written as, and then this is the crux of it here, where beta is the vector coefficients, sigma is observation error, y is the vector of observations. And then how do we read that thing in the middle? Well, we're just listing off all our parameters, conditional on the data, is proportional to, and then the likelihood times the prior. So the data, conditional on the parameters, multiplied by the probability of each parameter. This gets a little more complicated if you have hierarchical model, because then some parts are dependent on some parts and so on. So it's very helpful for hierarchical models to write that out. It's near the end of this book, and they work through some examples of how to do that with hierarchical models as well. And I've written out there at the bottom how I would say that equation there that you see. So what else to report? You need to justify your priors as needed, document any prior predictive checks that you did. Most people are not doing prior predictive checks. We should do it more. Most people are not. It's great if you do. Anything is far better than nothing. And I wouldn't get too caught up on justifying your priors. It sounds scary. It sounds hard. It's really not in practice. I've never had any reviewer ever complain about a prior. There's a lot of priors that are pretty standard, like the ones we've used here. As long as they are plausible, people are generally not going to question them unless you get into informative priors, and then absolutely you need to justify them more, ideally with some prior reference. You need to document your model building process. So we didn't talk about it in this terminology, but Andrew Gelman likes to call it the garden of forking paths. There's all sorts of decisions we make when we develop our models. And if we're not honest about all of those things that we've checked, it's very easy to find your way into a model that tells you what you want to know from your data, and that is no longer necessarily statistically valid. So if we want to build up our models, we want to be honest about the models that we have considered. A fantastic way of showing that would be that visualization I showed at the end of that workflow set of slides. Maybe that's a bit aspirational, but at least be honest about what models you have considered. State what MCMC algorithm you used, how many chains, how many iterations per chain, how much warm-up, how the chains were initialized. By default in stand, they are initialized randomly from dispersed starting points. I think it's -2 to +2 on the internal transform parameter scale. You can just say that they were started dispersed random starting points. So this is kind of boilerplate stuff. You got to say it, kind of boring, but you got to tell people how you sampled from your model. State how you assess chain convergence. So I would say the three big ones that I would expect to see would be something about that all our hats were less than 1.01. All effective sample sizes were above whatever, hopefully above 300 or 400. There's a citation by that Vitari paper that we've used throughout when we talked about effective sample size that you can cite for those particular thresholds. There are other thresholds that have been proposed earlier in the Bayesian data analysis book, but they've since made them stricter than what they suggested in that book. Document your posterior predictive checking. Lots of people don't do this as well, although more people do this than prior predictive checking. So any posterior predictive checking is awesome. Do some. Show just enough to convince the reader that they can buy into your model. Probably in a supplement. Probably nobody wants to see this in the main paper. Visualize your posterior distributions. Various ways that we've talked about this to show the full posterior, or at least summarize it with a point and a credible interval. Make inference and state your inference. And share your code. Most of this can be brief. It can go in a supplement as needed. Importantly, I want to hammer home, don't treat your results as frequentist. You can do better now. You've already done all the hard work thinking about your model. Making sure that your model is computationally faithful. You've done your posterior predictive checking. You've done all the hard work now. Don't just talk about your results being significant or not significant or having just some p-value. You can now talk about your parameters probabilistically. It's the thing that we always want to do, but we're told we can't do with maximum likelihood methods. You can now do that. You can say, there's such and such a probability that my parameter is above some threshold. Or there's some probability that my parameter is between this or this, or I can show the full distribution of it, or I can show the credible interval. You can talk about your parameters probabilistically, which is a fairly natural way to talk. So talk about your results. Use the full Bayesian posterior. You can get creative and you can quantify things that you want to quantify, even if they're derived variables, as we talked about. You can multiply, subtract, add, compare posterior samples. As long as they're coming from MCMC chains, you can easily summarize probabilistically to say the things that you want to say and attach probabilities to them. Okay, so some books. So this book, the Bayesian data analysis book, it's really the closest thing that the field has to a Bible. It's been massively influential. There are 3 editions. Fairly hard to read probably, unless you're a statistician. It would appeal to someone with a strong statistical math background. Not light reading. Probably more readable than you think. It's not really that bad, but there are probably easier introductions. This book, Statistical Rethinking by McElrath. So McElrath, I quite like his style of teaching. He also has his lectures available online on YouTube. He's taught a course based on this book several times, and you can look that up. It goes into lots of depth. There are several editions. This is the 2nd edition. It's a fantastic complete course on how to think about applied Bayesian data analysis. That the opening example with the the sampling of the Earth. That came from his lectures and from the book, as an example. It's not super technical or mathematical. One big caveat is that it uses the author's rethinking R package, as it's called, and that was really written for the book. It's a great sort of pedagogical tool for learning Bayesian models. It's not used in applied Bayesian data analysis very frequently, to my knowledge. There's no reason why it couldn't be, but it's just not widely used. There is a BRMS translated version of the book online. If you just Google BRMS Discover Rethinking, you will find it. This book by Hobbs and Hooton is fantastic. I've got that book right here. It kind of gives you the full theoretical background you're probably missing on probability theory, MCMC sampler theory, and how to think about Bayesian models. It's written by two ecologists, so it's written from an ecological perspective. There's no code, there's no data analysis. The math is actually quite approachable, and it's really an excellent resource as well, as I talked about earlier, for how to write your models to better understand theory and how to think about building Bayesian models. So, excellent resource, not a very thick book either, and I think it filled in a lot of holes in my understanding, for sure. And then finally, regression and other stories. So you might have heard of Gellman and Hill back from 2007, 2008. That's the top one there, the yellow and black book. That's sort of a classic in regression hierarchical modeling. So they sort of revised that and they're making it into two books. The first book is the one they call Regression and Other Stories. And there's a second one focused on hierarchical modeling that's coming out in the future. It is focused slightly on social science and political science because that's the background of Gellman and Hill, but still very useful as a non-social scientist or political scientist. Very readable, very practical how to think about data analysis. It uses RStan ARM, not BRMS, but the principles are the same, and there's lots to learn from that book.